Well, good afternoon, everyone. We're so happy to be here with all of you. My name is Jill Ford. I'm the Assistant Dean for Student Success here at the Plessy College of Engineering and Integrated Design at the University of Texas at San Antonio, otherwise known as UTSA. So you hear me refer to it as that. That's who we are. And we're really excited that we have the opportunity to collaborate with the D. Howard International Education Foundation on this wonderful initiative called the Rural STEM Initiative. We've been partnering with D. Howard International Education Foundation for quite some time. And our fearless leader, which is Mr. Wayne Fagan, was not able to be here with us today, but I am happy to sort of represent both entities and excited to be able to have this presentation. So we're here today with Delta Elementary School, and as I've just learned, the Gators in, I hope they say this correctly, Bay Minette, Alabama. So we're really excited to be here with you. A big wave out to all of our wonderful fifth grade students at Delta Elementary. Hi, everyone. Excited to be here with you. And now I really have the pleasure of introducing our presenter today, Mr. Sam Ximenes. And Sam is the founder and board chair and space architect with WEX Foundation, a very well-known foundation here in San Antonio. We've partnered at UTSA with WEX Foundation in other areas as well. So excited to hear from Sam. So this is a real treat for all of us. I also want to mention that the WEX Foundation is also one of our collaborating organizations with the D. Howard Rural STEM Initiative. So excited to be here. And Sam, I'm going to turn it over to you. We're excited to hear your presentation.
Well, thank you very much. Appreciate it. I'm glad that you invited me here. I'm always happy to talk to our younger generation of space explorers. Hopefully some of you will become those explorers, and that's what we're all about at the WEX Foundation, is to advance your careers in space. And we have programs that here in San Antonio and even nationwide that helps to do that as well. So today I want to talk to you about space architecture and what does that mean? You know, I think most of you all know what an architect is, what an architect does. You know, they build buildings and design cities, and they design, you know, planning for, you know, for urban environments and even, you know, schools and all that, you know, just the basic work of an architect. But a space architect works in space, the building in space. How do you live in space? How do you live and work in space? How do you build buildings and habitats and homes and structures for when we go to Mars and when we go to the moon and when we actually live in the space stations? Now we know we have a space station already orbiting around the Earth right now. It's been there almost 30 years. It's we've had continual presence of humans in space for going on 30 years now, and we're moving on to stepping off the this planet onto the next planets, the moon and then Mars. So that's why we need architects there as well. We don't just need engineers. We don't just need scientists. We need everything. We need cooks, we need lawyers, we need artists, we need biologists, we need people and medical doctors, and we need architects. So these are all opportunities for how you can think about your future careers as in the space world, in the world of exploration. So to give you some background, I'm just going to go through some pictures here of what does it mean to be a space architect. And I'll start sharing the screen here. 1 second here. Let me get it up. So hopefully you can see that in the presentation mode. Let's see. There we go. So I call this from dust to gas. And why do I say that? Because when we go to look for how we live on new worlds and how we build there, we got to think about the smallest particles, the finest dust grains, because all the way to the gases that we're going to need to use to breathe. So we use the dust essentially for building materials. You know, moon dust. Think of that. Think of moon dust and the fine grained sands. If we can take that and live off the land that way. We don't want to build all our building materials with us. I mean, bring them, not build them, but bring them from the earth, because it's going to be too costly and too expensive. So we want to use what's there already to build, just like when our ancestors came to America and they had to go across the prairies. They made mud huts. They made wooden log cabins from what was there. Well, the same principle. We want to take what's there on the moon and on Mars and try to use those minerals, those materials to start building. And we don't have trees, we don't have grasses, we have different kind of materials, and we have to do a little bit more technology development to pull them out of the grains, pull the minerals out of the grains, pull the water out of the frozen areas where we have found them at. So let me just talk about 3 organizations that are trying to help learn about how do you live on another planet. One is called Exploration Architecture Corporation, or XARC. You see up here on the top screen. And then there's Astroport, and then there's the WEX Foundation. So XARC are the architects, essentially, the ones that do the planning and the concept design. And Astroport are the builders, the ones that do the building and the actual construction and the material technology. Think of XARC as the architects and Astroport as the civil engineers for the building. So little background of what that means in terms of space architecture. We work in what we call domains of architecture. One is planetary surface systems. How do you actually build these buildings and these habitats on the moon and on Mars? How do you design them? How do you design them for humans to live in these buildings and whatnot? On the surfaces, on the planetary surfaces. The other is orbital architecture. How do you design a space station for humans to live in space, in microgravity, where there's no gravity, where there's the absence of gravity, and you're floating around? On the planets we have here on Earth, our normal gravity, but on the moon we have 1/3 gravity. I'm sorry, on Mars, 1/3 gravity. On the moon, 1/6 gravity. So those are different things you have to accommodate when you start designing, the height of buildings and the reaches for your workstations and those kind of what they call human factors. And then there's also space architecture works here on Earth as well. We're not just on the planets and in outer space, but we actually have to deal with supporting the space operations that go into moving off the planet, such as the use of spaceports. So we design spaceports here on Earth, and that's also part of our space architecture career and domains. Some of the projects we worked on here on Earth, just to give you an example, in Houston, there's a spaceport. They have a spaceport called the Houston Spaceport it's being developed for spacecraft to take off from, and for manufacturing and high technology businesses. How many of you heard of Virgin Galactic? Richard Branson and Virgin Galactic. He's a real billionaire that wants to take tourists up into space, for a couple $100,000, if you could afford that. You can actually have a ride to space and be an astronaut for 15 minutes, and you get that ride. But for him to actually take those planes and that spacecraft up into space, he's got to take off from somewhere and land from somewhere. So that's the spaceport, and that's what we do too. So we build the spaceport part of that for him, and that's the architecture role in the space exploration business. And then there's also the military role too. So the military wants to think about how do they move cargo and all their people from for a human disaster, for example, for humanitarian concerns. When there's an earthquake or a big disaster somewhere, we want to get material somewhere real fast. We're thinking now about using rockets. Elon Musk and his Starship. If you heard of him, I'm sure everybody's heard of Elon Musk and his rockets and his electric vehicles. Well, he's also developing a rocket that goes from point to point. In other words, from one place on Earth to another place on Earth in under an hour. And this big rocket he has can carry 100 tons of cargo in under an hour to anywhere in the world. And we're developing those systems too. How does that work? How does he make the logistics of that work? The ground support part of that, to bring material to emergency material to someplace. Then there's the construction part of it. So this is now the Astroport company that deals with construction. How do you build on the moon? how do you actually take the material there and start building? How do you bring those robots that we're going to need to have and make those robots autonomous? Autonomous means no human involved. It's all automatic. It's all a robot doing everything by remote control or by programming, and that's a pretty hard task from 300,000 miles away, 250,000, 300,000 miles away is here on Earth. Somebody controlling the robots, on the moon, and even further on Mars, which is another even harder problem because it's going to be a time lag in terms of communication. And what the Astroport company is doing is they're learning how to build landing pads. The landing pad is one of the first things when we talk about what we call infrastructure. The infrastructure you need to have for living. This is the basic communications and the roads and the basic power systems that you need to put in place to start living there. But before you can even put those roads and those power systems and those habitats, and you have to deal with give me 1 second, please. Sorry about that. You have to deal with the ability to land and take off. And if you're going to be there for a permanent basis, you're going to be doing it a lot, right? You're going to have to bring resupply missions. You have to bring food. You have to do crew change out. But if you land right on the ground, that's a problem on the moon because it blasts out all that dust, those rocket engines make a huge plume blast, they call it. And that high energy of those fine sand particles can go even up into orbit around the moon. And if they go into orbit around the moon, then the other spacecraft that are coming and going they're dangerous. They can cause hazards and disasters. So we want to make safe landing pads. And that's the first thing you have to think about when you start landing on the moon for a permanent base, a human lunar base. And that's what Astroport is doing. It's learning how to take that regolith and how to make a brick out of it and make landing pad bricks. And I'll show you more about that later. Now, the other thing that we do is the WEX Foundation. Myself, and my generation, we're not going to get there. We're going to have to rely on you guys. You're the generation that's going to be there. You are the generation that's going to be on the moon and on Mars. And we have to rely on you to bring that technology and that knowledge to help us get off the planet and learn how to live on these different planets and expand our civilization into the solar system. So we at the WEX Foundation develop programs starting at the 6th grade level. I think you guys are 5th grade, right? So by next year, with our programs, if you were in our area or in one of our other schools that we are involved with, we start bringing you into the knowledge of what it takes to be an explorer by learning about space and and the engineering and the science and not just, again, like I said earlier, the arts, everything that can be used for us to start living in space. One of the ways we do that is we teach you how to build your own science instruments, your own engineering robots, and you build them, hands-on projects with teams. And then we take you into caves here in our area. We have these caves around the Texas area that are analogs to lava tube caves. And I'm going to talk about that more. About where do we actually want to live when we go to the moon or to Mars, and caves that are already been discovered is one of the main things we are looking at, is to help us protect ourselves from the harsh environment, the radiation environment, the micrometeorite environment, the constant bombardment of small particles always hitting the soil, the ground. And we want to figure out how to use those caves as our habitation area. So we have caves here in around the Texas area, and we take our students that have designed their instruments, and they go into these caves and they learn how to do field measurements like scientists, measuring different types of samples of air and quality or just microbes or whatever their project is about in the caves, and learn how to explore in these caves as well. And it's a pretty good 3-year program. I'll talk at the end. I'll talk more about what that's actually involved with. So where do we want to go? Okay. One of the things right now, NASA is going to go to the South Pole because that's where the water is. They've discovered water in in what's called the permanently shadowed regions. These are craters that have been bombarded with asteroids from or meteorites from long time ago, and they've never seen the light of day. And we believe that there's water at the bottom of those pits, the frozen water, and that's what they want to start doing is mining that water. The water is going to be important for us wherever we go. We want to find water. And also at the South Pole, there's a constant sunlight, almost constant sunlight. The moon, you have the two diurnal cycles, 2 cycles of 2 weeks of daylight and 2 weeks of darkness. And that's problematic for your sun, the solar arrays. But at the South Pole and North Pole, you actually have more constant sunlight. You have almost 24 hours of sunlight. And that's what makes that attractive. But they don't have the caves over there yet. We haven't found any caves on those poles that we are certain of. There's a few that we think that may be there, but we're just not certain yet. Some caves we have found on the moon, more on the equators of the moon, what they call the equatorial region. And these caves are all actually, we find caves on all the planets. There's caves on Mars, caves on the moon, and even caves on Earth, of course. That picture at the bottom of the screen down here, the colored one, is that this is the biggest cave on Earth right now. It's in Vietnam. 48 meters in height. It's a pretty big cave. That's about the size that we think the caves on the moon are about here. And we found one here called what we're starting to look at is what we call our case study. We want to use this cave as a benchmark for what it takes to make those technologies we need to become viable and prove out the concepts for entering into the cave. This cave here is called the Marius Hill Skylight. It's at the bottom of a pit, a big deep pit that they found on the moon. That was just discovered about 10 years ago. You can see there the small little hole here. That hole, not really that small. It's about 100 and about 60 meters in depth and 80 meters in diameter. I think those numbers are right. I'm going to have to check myself on those numbers, but it's a pretty deep hole, and we think that's a good area to go and investigate. Because what we want to do, we want to get down to the bottom of it, because at the bottom of that hole is a cave, a lava tube cave. Now, lava tubes were formed billions of years ago when the moon was still volcanic and had activity of lava eruptions. And when the lava, I'm sure you've seen lava eruptions here on Earth. There was just one recently in Hawaii. That lava flows out of the top of that volcano and starts flowing down the hill. As it continues to flow, it starts hardening on the top of it, and the bottom of it the lava will continue to still be molten and flow through it, so that when it finishes it leaves a cave at the end of it. So that's why you have a hardened surface at the top of it. And this hole is the result of one of those pieces of that top of that lava flow having collapsed, and it then exposes the cave at the bottom of it. So that's where we want to try and look at that as a way to go, and maybe at some point in the future put a dome around it so we can start living there with more volume for living and moving around. And these are kind of the urban planning, that, if you will. It's kind of a term that just borrowing from Earth here, but it's really, how do you plan out that base? You need to have, of course, here's where we want to start living in it. We want to get down to that cave and put a dome around there. We want to bring our habitats, the first habitats there, and start being able to live in that area as well. The construction shack, basically. We want to have our landing port, okay, our landing port there, so that we can, bring our supplies there. We want to have our nuclear reactor or for our power supply system there, solar panels. And we want to start mining. We got to start mining the surface of it as well to extract the oxygen out of the regolith. The regolith is when I say regolith, I mean moon dust. That's what the term they use for the moon soil, the moon dust. It's called regolith. And in that regolith, there are many things that we can use, such as water, as I mentioned before. There's oxygen in there, so we want to extract it, mine it, extract it, store it. We could use it for rocket fuel. We could use it for breathing. Air and just basic, oxygen production aspects of it. So those are the things. That's the kind of things we will be doing there for for the economy we would be developing there. So how does that happen? It doesn't happen right away. Okay, it's going to take a long time. It's going to take a century. I have a 100-year plan here. By the end of the century, it's, you know, we probably won't see that big dome there until the end of the century, but we got to start somewhere. And you know, the first thing you do is you start doing it by remote sensing with the satellites we have there right now. Our satellites that are already orbiting the moon can detect where the minerals are and can detect the topography, you know, where the big rocks are for, you know, to get out of the way of when we start landing there. The next stage is the exploration stage. This is going on right now. You send our robots there. These are just the robots that we send to go and explore the caves and find out what's there. They will explore, you know, and tell us, you know, what the topology of what the cave looks like. After that, then we will send the next phase. This is probably going to be by the time you guys are in, probably getting out of college, I would think, or starting your careers, when you start sending the humans there, the humans and the robots together to explore the cave and ground truth what the robots found when they first got there, to see if that cave is really a good spot or not. Is it structurally sound? Does it have the right things that we want it to have for living there? And then when we say, yeah, okay, that's a good place to go, then we start bringing in our habitation modules and we start living there a little bit at a time, a month at a time, 7 days at a time. Because again, remember, we don't have any infrastructure at this point in time. We have to bring everything with us. We have to bring all our food supply and all our air and whatnot. So we can't stay there, you know, constantly. We have to change out crews and bring in new crews. But these are small modules that would be in there, and we start, you know, doing our explorations and our investigations and our ability to understand, you know, what are the challenges for living there. Well, after that phase, this is probably by 2040, 2050 timeframe, middle of this century. You guys are still alive, still, you know, at the height of your careers, already having your own kids by this time. So now we start thinking about long-term permanent stay. You know, how do we make this a settlement where more than 7 crew members can be there? Maybe we have hundreds of people living in there. And now we bring in the big infrastructure. We clear out that cave. We bring in the power systems, and we bring in make a big, huge spaceport, and we have the ability to stay there for long periods of time. So that by the end of all that construction phase, by the end of the decade, then we can start thinking about building that dome on top of that hole. We get out of the spacesuits, we get out of the cans, the habitats. We can move around freely at this point in time. And I think this is all happening by the end of the century. So I'm gonna show. Hopefully, I'll be able to show us a quick video here of kind of that concept here. Give me a second here if this will work or not.
The closest celestial body from the Earth, Earth's only.
Can you hear it?
Yes. Yes.
Okay.
Satellite, the Moon. The Moon now becomes a station for humans to travel into what was considered outside human limitation, space. The beginning of a new future, lunar construction.
Well, one note here. I'm just going to warn everybody. You're going to see a Korean flag, not a U.S. flag in this video. And the reason for that is this was done for a client that I had. The Koreans also want to go to space, and they're building plans for doing that as well. Not only the Koreans, but many countries around the world have plans to go back to the moon and build and learn and explore and mine the moon for resources. So this will probably think of this as an American venture, but right now the Koreans are on our side, so it's going to be an international endeavor. So if you see the Korean flag, don't get freaked out. America would be there first. Okay, thank you. Just a disclaimer.
A lunar orbiter launched from Earth enters the lunar orbit. It initiates remote reconnaissance as it explores the lunar surface to identify sites for construction. It collects and analyzes geographical, resource, and environmental information, identifying the most optimal location for construction. A robot for more detailed reconnaissance arrives at the construction site. The first task of the robot is to go over the ground and with its camera collect detailed geographical information. And with its exploration drill, collect geological information. It also confirms the location of a safe lava cave for human habitation. Another robot conducts construction material testing with the moon's resources. The robot's thorough and comprehensive reconnaissance is an imperative step of evaluating and verifying technology before actual lunar construction. Based on this verified technology, robots with construction equipment make their landing. The first step is to set up a power station for energy supply. And next is the construction of a landing pad to prevent the occurrence of dust, which could be deadly for astronauts. And the construction of a blast wall for protection from meteorites. This is the lava cave, confirmed in Phase 2. It is the optimal place to keep safe from the strong radiation and meteorites flying around space. And it is where a habitation zone will be built for humans. Finally, the lunar station construction phase. Astronauts arrive and safely enter the lava cave where humans will habitate. Roads, an advanced base, and power station for both habitation and development will be constructed. Overcoming severe environmental conditions, this will be the completion of the city of the future humans have dreamt of. Based on the rich energy resource of the moon, we are preparing to travel further into space. The endless challenge for a bigger world. The research for the future continues on.
Well, as I mentioned, that was for a client I had in South Korea. They had plans. They're trying to figure out what does it take for them to participate in the space program. So, and that was their what we thought their role would be for us to help them figure that out. Okay, so let me see. Are you seeing the presentation again? Yeah. Okay. All right. So let me go back into lunar soil, lunar dust, moon dust. When we work with moon dust, we think that we can pull out minerals like metals and like magnesium and iron and titanium and gases, as I mentioned earlier, like water and oxygen, and then we can turn it into bricks and rebar. So what we're doing here, we're making this moon dust into lunar bricks. These are bricks we're doing right now here at Port San Antonio and at Astroport. Is we're making this furnace to melt that regolith, that moon dust, into bricks. We're looking at we have to make those into a certain shape so that they're interlocking, so that they can land on that landing pad. One of the things we're doing is developing the robot that's going to make that happen. So this robot is a unique robot that can place the brick at the same time it forms it and makes the landing pad. And that furnace you see there here's one of our first prototypes that we started developing. We're making those bricks out of that moon dust. You see here we had, and then the other thing we had to figure out is how to do that in vacuum. We can't just do it here on Earth. We got to understand that, can we make the brick in a vacuum, like the vacuum of the moon? And this, we do testing of those bricks, as you know, in our vacuum. This is our vacuum chamber here, and we've been doing our first test, and we've been able to find our first vacuum test of a brick just this last year. The other thing we're trying to figure out is how do we take that same moon dust and we can 3D print with it. So we're able to take the filament, like you ever worked with a 3D printer, and 3D print our habitats and 3D print real fine detailed work as well. I don't know if this will show you. This is a picture of a. No, it's not going to come out. No, I thought it was another picture. Okay, that's a picture of a printer we're making. It's called a hang printer that allows us to print large scale. Sorry about that. I don't have the video for it. But you know, we're also doing things like learning how to make the robots and building the habitats. We have designs for our habitat designs that are going to be for Mars and for the moon. I want to show you another video that talks about our LEDO mission. The LEDO mission. Let me just stop here, okay, and just see if there's any questions before I go on to this next phase.
I have questions for him. Ethan, okay, speak loud.
My question was, it was like whenever it was from the beginning, you said there'd be like a time glitch or something. What is that?
A time glitch?
Yes, sir.
I'm not sure what that was about. The time glitch. I'm not sure if I recall what that meant. Yeah.
Sam, I'm thinking it was when you were talking about Mars, the communication glitch, because the amount of time
yes.
communicating Mars back to the Earth is what I think it is.
Right. Yeah, that is correct. So it's a delay, not really a glitch, it's a delay. So because it takes so long to, Mars is so far away, it takes almost 20 minutes for a signal to reach Mars and then return back and then get an answer. So another 20 minutes. So every time you've probably seen the Mars robots that are up there right now, whenever they communicate with them, it takes 20 minutes for that signal, that message to get to that robot. And then it has to answer whatever the question was or whatever the query was, another 20 minutes to come back. So that's the time delay. And because of that, we can't do what's called teleoperation, where we can control in real time the robots. They have to have their onboard processing already programmed into them to make them autonomous. That's what's called the time delay. From the moon to the Earth, it's not that bad. It's only like a couple seconds of time delay. It's still a little problematic for teleoperation, but it can be done. But we have to adjust for it. But Mars is the harder one.
I have one more question. Speak loud, Roman.
Why do we have to, if we ever live on Mars or the moon, why do we have to live in like caves?
Well, we don't have to live there, but it's the best protection because there's a harsh radiation environment. Because the moon, in the case of the moon, there's no atmosphere, and the radiation from the sun can basically destroy your DNA, can kill you if you expose long enough. And that's why astronauts don't stay very long up in the space station. They have to come rotate. I think the longest astronaut stay has been about a year, maybe a year and a half. But the radiation is what we want to protect ourselves from. And if we lived on the surface, we'd have to bury our habitats on probably about almost 3 meters, like 9 feet worth of dirt and soil on top of it, so that we would be protected from the harsh radiation environment. And the caves provide that same sort of protection without having to do all that construction, that excavation of pulling that dirt up, on top of all the habitats. Well, it will be a combination of both, living on the surface and living in caves.
Aubrey, how can you find the caves on land?
I'm sorry, I didn't hear it. How do I find the caves?
Yes.
So there was, in 2007, there was a satellite called the Cayuga satellite. It was a Japanese satellite, and it was doing remote sensing. It was doing, it had a sensor that was able to detect, and also a camera that was essentially mapping the surface of the moon. And it came across, when it came across that area, it discovered something different about wasn't a normal crater. It was something deeper than a crater. And there was essentially, it's by remote sensing is how you discover the caves. And they've discovered almost 200 of them on the moon already. And on Mars, I think there's almost the same number on Mars as well that they've discovered. Mars has even bigger caves, larger caves than on the moon.
Okay, I think that's all the questions.
All right, so let me show you this video here. It's of a what we call our Lido mission concept, and what it shows how our idea for how you get into the cave, and using our robots to explore it with these we call our mule robots. These are multi-utility legged explorer robots, and they're the first robots that go there to explore and map the cave out with a 3D point cloud, they call it, so we can see what the three-dimensional shape of the cave looks like.
Before humans can inhabit the moon,
Again, are you hearing it now?
Yes.
Yes, okay.
EXARC and Astroport plan to deploy specially designed robots to explore the lunar cave, where astronauts will eventually live and work. The Lido 1 mission is named for the mother of Artemis and Apollo in Greek mythology. Just as Lido sought a place to give birth to her twins, so does the Lido rover seek out the location of the birthplace of our lunar settlement. This reconnaissance mission involves an autonomous rover that will investigate the selected site, called the Marias Hills Pit, where the lava tube caves are located. To respect the site during first contact missions, it's important to use exploration technologies that won't disturb the pristine site that has existed for billions of years. The rover will initially land at a distance, behind high hills or other geologic structures found in the area. But carefully choosing where we land will protect the pit from rocket exhaust and plume blast material. In this way, scientists and geologists can take uncontaminated, accurate measurements of the pit and caves. After landing, the rover then travels to the lunar pit and secures zip lines. Next, the rover will deploy its payload that will aid in relaying key data about the site. The payload is a set of twin mule robots. MULE is an acronym for Multi-Utility Legged Explorer. The mules will bring cave measurement tools, cameras, power, and communication lines. They'll explore the cave to collect important data, including measuring the entire area to create a 3D map of the lunar cave and detect if gases and water vapor are present. The Lido 1 mission prioritizes preserving the lunar cave for the second phase, which will bring humans and another set of mule robots. The robots work together. For instance, when the first mule runs out of power, it notifies the second mule. That mule is tethered to the payload module to allow for power and data transfer. The second robot is also equipped with an arm, so it can unsnag itself if the cable gets tangled in transit. The mission objective is to do a comprehensive site survey to gain an understanding of the pit and cave characteristics. This will help determine the suitability for future habitation and the eventual creation of a lunar settlement. The hope is that the explorers and scientists will travel deeper into the cave to conduct their research and confirm the structural stability for the future permanent habitation modules. The data transfer goes back to the payload box and is relayed to scientists monitoring the mission back on Earth. When the Mule robot's mission is completed, they will power down. They can be revived and repowered for use in subsequent human reconnaissance missions. Once the site surveying is complete, we'll set up a base camp on the lunar surface and construct an elevator platform to lower expandable modules down the pit and into the cave for longer stays of months at a time. Eventually, landing pads, mining operations, habitat construction, and power stations will provide the basis for a permanent lunar settlement. In many years' time, the goal is to construct a dome over the pit so that the inhabitants can get out of their spacesuits and leave the habitat modules to move about freely in breathable air.
So that was I think a better view about how to take care of the cave exploration part of it. There's another set of videos that go with that if there's time I'll show one more of it. Let's see. Where are we here on this thing? Okay, this just talks about, how does that habitat get down there? You have to bring in a portable habitat, and it unfolds. This just talks about you have to, how do we get the gas in there? How do we get our breathable air inside that cave, inside that pit? It takes almost 88,000 cubic meters of gas. And where does that gas come from? Well, we have to mine it. Okay, we're gonna have to mine it out of the regolith on top, out of the moon dirt to make the air. And then one of the ways we test the moon dirt to make sure it doesn't leak out is, does the moon dirt have enough density that it can prevent the gases from leaking out of the dome? And we do that with certain instruments. So now I'm going to go into Mars. Okay, this is the Mars base. Mars, not Mars base itself, but the Mars exploration technologies. This is one thing we were looking at, is how do you 3D print a habitat on Mars and understand how does a crew of 4 people live? As an architect, we have to understand how people live together, and and can live there for 2 years at a time or a year at a time without going stir crazy, basically. And you have enough space, and privacy, and community space as well. So these were just studies in terms of how do you make a minimum amount of area available for a crew of 4 to be able to live and work together. And those were the first studies we started looking at. Then we started looking at another one called the Mars Hex Hab, which is a little bit bigger. It was more of a 3-story building. Another was the ability to 3D print as well, and then provide again, these were the studies of how do you outfit this 3D printed habitat, and be able to again work with a crew of 4 people working together, and then also have like hydroponics and greenhouses there as well. You can see here how we had to figure out how to, as an architect, you got to deal with all the same things you do when you build a house. How do you put the air conditioning system in there? How do you put the plumbing in there? How do you put the electrical plugs and cords and all the wires? How does that get put into these habitats? It can't be done autonomously at this point, but we have to try and figure out ways to make that happen. So those were the kind of the challenges for building these habitats. Then how do you actually construct it? How do you excavate it? How do you get the machinery up there to make it work out? What's the phases of the growth of it? Is it able to to grow from one to many, so that you end up with a community? Then the construction equipment. These are the same problems we have on the moon too. But how do you excavate? How do you bring the material that we need to have? Again, this is now Mars dust we're talking about. On Mars, we can actually take the Mars dust, the Mars ground, earth or soil, and combine it with with carbon dioxide that's in the air of Mars. Mars has a thin atmosphere, and it's got a carbon dioxide atmosphere, and we can pull that oxygen out, that carbon dioxide out of the air, and turn it into a 3D print material for 3D printing the filament as well. So here, things we do. This is all pretty pictures and all that, right? This is what we call PowerPoint engineering. But those aren't realities. That's not the real stuff. Those are just concepts. These are the beginning stages of how do you start thinking about how do you start building this and developing that technology here on Earth. These are some projects that we work with our students at UTSA. That we sponsor student teams, and they've been able to build small robots and do testing of a compactor, for example, and how the wheels get stuck, not stuck in the lunar soil. So these are real world tests that we start working with to start understanding, these concepts and turn them into reality, turn them into real technology. One of the things we have to figure out is, how do we do all this excavation? We're building robots to dig and to compact and to sieve and essentially level the ground for making the foundations for the landing pads and for the habitats. One of the things to do that, though, is we have to build our own test bed here on Earth. So we're working towards building a large test bed, what we call a lunar proving ground, and we're gonna kind of mimic what we find on the moon by making a similar terrain out of that moon dust. And by the way, this is not real moon dust we're working with right now. Of course, we don't have that moon dust. We work with a simulant. It's called a simulant. It's a basalt material that's similar to what we find on the moon. It's got the same mechanical and chemical composition as what we find on the moon. And we take that and we're going to make a big dome, and we start. Our plans are to build this lunar proving ground and start testing here on Earth the robots before we can send them up there. So you got to start doing all this tests and understand how it works here on Earth, and try and simulate the same environment that you find on the moon. So now I'm going back to our LCATS program and what it's about. This is the program, just to give you an idea of what how a school can become involved with teaching kids about this and students about space exploration. We take that same. You recall in the beginning I talked about the phases of the lunar base development, from the first phase all the way to the last phase. We take those phases, and every phase along the way has a different technologies that have to be developed. So we use those as the basis of our student curriculum. And again, I mentioned about going into the caves. I don't know if I should show you. I'm just going to show you this. We might have some time for this. This is a good video about what that program is about. You can see this.
Hey, San Antonio, Google Fiber is expanding in your area. We're bringing award-winning gigabit internet to
LCATS, lunar caves, analog test sites. I have not seen any program that begins at the middle school level that is what we're offering to students who are interested in space science. Our students are potentially with us for 4 years to be researchers, engineers, and to work with scientists, researchers, and engineers, and work on a project that's meaningful and that is an analog to a NASA space mission.
As I look out here, I'm seeing really the realization of an idea, of a dream, to make San Antonio a space community.
As a research scientist, I see potential in my lifetime for us to discover life on other worlds. The LCATS program seems like the real world. So kids can learn skills, they can become interested in things like math and science and engineering. This is very much modeled after what NASA does, We tried to make positions for student teams that were analogous to what we see in the laboratory and in space programs, things like the chief engineer or the systems engineer or principal investigator, scientists, technicians. Everybody has to work together. It's a cast of thousands that makes these space missions work.
We have a location on the lunar surface, the Marius Hill skylight, for them to begin to research that. What does it mean? What are the challenges that you would face in commercialization habitation? They are learning about temperature readings, carbon dioxide, types of things that you have to consider if human life could live in that environment. They're going to go in the robber baron cave. They're going to be using LiDAR, which is to map the caves. So they'll have an experience, an analog experience, explore the cave, use the sensing technology, see how it works, and then eventually that technology they learn about would be deployed on an autonomous robot. And we're sitting here at Mission Control Scobie Education Center, the idea being that a ground-based crew would be at our analog robber baron cave, and here would be the mission crew that's running the mission to autonomously deploy the robot in that location and collect that data and bring it back.
So we have no reason not to believe that we aren't going to find life somewhere here in our solar system in the conditions of places like Europa, Enceladus, and Saturn. So we're trying to convey that and get the kids excited about it, and give them a taste of what the real world is like in space exploration, space science.
I just know that one of our students is going to set foot on the moon, on Mars, on an exoplanet. I know that they're going to put San Antonio on the map. They have so much potential. So 20 years from now, I just want to sit back and just get the joy of seeing how their careers have progressed, and maybe, just maybe, how this opportunity was what gave them the little push or the little extra knowledge that made it happen for them.
So it's not just for San Antonio. This is for everybody. Your school could be part of this as well. Could have a similar sort of program as well. Or any school in the nation can have this program. So that's kind of our goal. And again, as I mentioned earlier, it's your generation that's going to be the ones doing this. These explorations. This going to be on the boots on the ground on Mars and on the moon. And that's why we reach out to you all. You know, the program it's a program where the first year you learn about the remote sensing. You have projects in remote sensing. You launch a high altitude air balloon into the sky and goes to the edge of space with your experiment. The second year you learn about the robotics, the reconnaissance. In the third year you learn about our space architecture and habitation. And then you can actually make a comic book too as well. That's out of your experience as part of the program. And we bring it to our test beds. You can take your robots there. You learn about how to make a robot that can enter into the pit and go down the holes. We also have again these high altitude launches that we can take your experiments on, and they could get launched on a balloon that goes up 100,000 feet into the air to the edge of space. Some of our students have even been able to take one of their projects that we thought was such a good project that we took it back to our commercial company and developed it for NASA. This is one instrument that it's a dust instrument where they learn how to measure lunar dust, fine grains of lunar dust accumulating on a surface. And we think this is such a good project that we made a proposal to NASA to put it onto one of their space lunar landers. That's what we're working on right now. And then we're looking on, again, back to space architecture. How do we build the systems here on Earth so that we can start doing the testing? We're figuring out how to make a big building so we can put these habitats in there and test, in real time, how to test the habitability for the astronauts. These are just more pictures coming to the end here of those other things you saw in those videos. One thing I want to get to at the end here is another part of space architecture, which is the orbital stuff. We began with the dynamic pyramids that have been with us for years and years, and now we have a space station orbiting the Earth right now. But this is a future space station where this is the future of what space stations could look like. in the very, very far future. So with that, I'm just going to end my, with any questions from here.
Wonderful. Do we have questions from our students?
I don't see any hands up.
I have a question about the LCATS program. How do you get enrolled in something like that?
Well, right now, we're going to start. Right now, it's just the LCAS itself is local to San Antonio, but we have another program called New Roads Await You that is more national, and we work with communities and schools wherever they're located at to be part of that program. The funding for that program ended though last year, so we're trying to revive it so that we can expand it into additional schools. As far as the LCATs, we're glad to talk to any school district to implement the program in their school area as well. So as far as LCATs for now, you'd have to come to San Antonio for that. But again, our goal is to bring it out to other school districts as well, and we're willing to do that.
And Shay?
So if y'all were talking about like making the domes, how would you do that if they don't really have a lot of gravity?
So the gravity part is kind of interesting because especially on the moon, you always have to deal with the of course the 1/6 gravity that's on the moon, and to make that dome, you wouldn't have to have all that, on here on Earth. You have to deal with the weight of the gravity, and you have to have a lot of structure, a lot of supporting columns, and a lot of ways to to support the huge weight of that dome. On the moon, you don't have that much of a problem. It's still a problem, but not as hard of a problem. And you can have larger spans to deal with. That's why we can go across that huge size of that pit, because the gravity actually works to your benefit. And I can see where you think about basketball, for example. If you think about a basketball court in the height of the hoop, and jumping up to get it. Well, if you jumped up on the moon, you could do a pretty easy shot at getting into a standard basket. But on the moon, you probably double the height of the basket because you're going to eventually be flying essentially on your own.
I also have one more. So how are you talking about like breathing on there if you don't really have a lot of oxygen? And plus, wouldn't like, how do I put this? Whenever you're up there and you're breathing without no spacesuit, sorry. How would you do that? The carbon dioxide.
Okay, so that's the reason for the dome and for the habitats. So when you have the dome on top of that big hole, then you pressurize it. What's called, you essentially fill it with air, like on an airplane. When you go into an airplane on a flight, you have a cabin, and when you get up to the height, 30,000 feet or 25,000 feet in the air, they pressurize it. They put air into the cabin. So that's what the same principle. You pressurize the dome so that you're inserting air, oxygen into that environment, and that gives you the ability to breathe the normal air, and that way you don't need the spacesuits. But when you go on the surface, though, you got to put your spacesuit back on.
Aubrey?
Is it easier to build on Mars or Earth, or not Earth, the moon?
I didn't hear the question. Can you repeat it, please?
Yes, would it be easier to build on Mars or the moon?
Well, right now, the moon, because it's closer. There are different challenges. Because there's no gravity, no air on the moon, that presents a lot of different challenges. And in that regard, because there's an atmosphere on Mars, it's easier. But because it's further away, it's harder. Because you got to, it takes longer to get there, and we got to do more logistics considerations. On the moon, that's why we're going to the moon, by the way. That's why the Artemis program, NASA's Artemis program, is going to the moon first, and then they're going to go to Mars. They're going to the moon to do all the testing. They're going to test how to live on a different planet and how to build construction aspects of it. because it's easier there because it's closer. We can make make mistakes without the big catastrophes to deal with.
And Shay,
So-
one more-
Go ahead.
What would happen if you had a leak in your oxygen tank? Would you what would happen?
Well, you'd want to certainly plug it up pretty quick. If you had a leak, you'd have to, depends on the size of the leak. You need to plug it up. Like on the moon, for example, if you had a leak, let's say the leak of the dome, a meteorite hit the dome and broke through it. Hopefully, by the time we have that dome built, though, we'll have materials that can withstand those impacts. Those are material technologies that we need to develop. But let's say you had a leak, okay, you would be able to put a patch on it right away, because the pressure that's inside the atmosphere would essentially put a patch that would make it stick to that hole, prevent that leak from going out. But you definitely want to deal with a leak. Okay, you do it also no matter what's in your spacesuit or your spacecraft or your rover, you want to make sure you don't have the leaks, because that's problematic, and you have to do emergency situations, contingencies.
Okay, I don't see any more hands up.
Okay, and I think we're just right at time as well too. So I just wanted to say a big thank you again to Sam for this wonderful presentation and all the great information that you shared. Thank you to Delta Elementary for participating in this program with us, and I hope you learned a lot and really enjoyed it. And thank you again to Mr. Wayne Fagan, the chairman of the D. Howard International Education Foundation, for helping to bring us all together here. So thank you all.
Thank you.
Thanks a lot. Appreciate it.